Hello there. We did make it to integration. This was my dream, hopefully your dream, because you might see some of this in a subsequent class somewhere, business, whatever, social sciences. We'll see. Let me know if you run into it again. If so, I'll try to make sure I get this far. Meantime, thanks for working so hard that we did get this far. We've got a few objectives here. You can pause and read these if you like. The most important one being, at the end, use antiderivatives to solve real-life problems. Well, maybe not your life, but who knows? You never know what you're going to end up doing someday. So we're going to call these antiderivatives to begin with because that's a tie-in with what we've done most of the semester. Derivatives, now antiderivatives, it just means we're doing it in reverse or inverse, you might say. So we're going to go in the opposite direction this time. Oops, a little fast there. Well, I guess I've already said all that, haven't I? So down here at the bottom, and I think I need to check in with a pen here. There we go. Down at the bottom you can see the function f is an antiderivative of functions. So let's get started down here. We talk about the function f. Now, if you're not careful, if you're like me, you might get confused. Okay, you've got an f and you got an f. Yeah, one's capitalized, one's small f. We've been using f for years as our function. Actually, this time, when you talk about which came first, capital F function comes first. And then later, after you take the derivative, then you get small f. So you might consider big F perhaps as the father of little f of x. I don't know. Whatever works for you. Just keep in mind that the derivative of the capital F is the small f. So you're going from capital F to small f. You don't want to get those backwards. That could be really confusing, trust me. So it's an antiderivative, then f of x plus c will get this derivative, no matter what that c is. Capital F of x actually belongs to a whole family of functions. So family of functions, that means if you put a 1 there, you've got another member of the family. Capital F of x alone, capital F of x plus 1 is another member of that family, capital F of x plus 2, and of course you could always put some decimal places there just for the fun of it. All those are functions that will give you a derivative of f of x. Now we've got some new notation here. Some of you already know about this integral sign. It's like a capital S that was stretched both ways. I don't see that much trouble making my integral sign. After about 2 or 3, you'll probably get into the hang of it too. So this is the integral sign. And then typically we'll have a function afterward. Let's just call this one h of x just for fun. And if it's h of x, then at the end you'll have d of x. So whatever this variable is here, you'll usually have d of x at the end. That means you're taking the integral of this function with respect to x. That's only important if you have more than one variable. Typically, in our case, we'll probably only have one variable, so these x's will be matched. But it's also possible to have different variables. So here's our indefinite integral. What that means is there are a number of functions that this refers to. This refers to capital F of x and capital F of x plus any real number you like. All of those together. And if you graph just several of these, you get the idea. Because if you're going to graph, say this is f of x, you just call it f. Then all the other ones will be parallel to that, sort of like this, following it, but either a little bit higher or a little bit lower. That's the family. All the same curves, but a different y values. So here's what it looks like. The integral of f of x with respect to x, and here's our function that came first before we got this derivative, and this reminds us that this is one of a big family of functions, and this is a constant of integration. When you've got an indefinite integral, you have to make sure you put the c out at the end. Get in that habit, because we're not going to go too much further. Usually we'll have that c out at the end. The differential identifies the variable of integration, just as I said. The x tells us which variable we're using. Finding them. Okay, we're finally on it now. So how do you do this? Well, first of all, one good reminder. Remember, this function you got because it was the derivative of something else. When you take the integral and then take the derivative again, you go backwards. So these are inverses. The integral and dx are inverses. If you take the integral and then ddx, you get a certain function out here. We'll call it g of x maybe. If you take h of x, take the derivative and then the integral, you're back to h of x again. Remember, these two, the differentiation we've been doing and the integration we're starting now, are inverses of each other. They undo each other. In this direction, when you take the integral, where's my cursor? There we go. Remember, you've got your constant of integration. Up here, when we're taking the derivative, remember the derivative of a constant is 0, so it disappears up here. Now, we've got some rules, not in a bad way, in a good way. These are pretty self-explanatory. In some cases, they're very much like the differentiation rules. For example, here's one. Here's a k in front of the x, so you can bring that k in front of here. Oops, wrong one. I was one ahead of myself. The integral of just k itself, k dx, you get kx, and always put that c at the end. Here's the one I was thinking of actually. If you've got some constant in front of an original function, you can get the same result from your integral if you slide that k out front. Find this, multiply by k, and you get the same result as if you did all this. Next one, as you might guess, if you have two functions that are added together and you're taking the integral of the sum, you can take the sum of the integrals. Or if you've got a difference of two functions and you want the integral of that, you can just take the difference of the two integrals. And then we get to a real power rule. This is like the differentiation rule. Remember, the differentiation rule looks like this. ddx, and if we're taking the derivative of x to the n, we get x to the n minus 1 and the n out front. On the other one, remember this is times and this we're subtracting. Do just the opposite and you got the integral. Remember their inverses? So you take this n, make it one bigger instead of one smaller, and the n itself, well, you switch to the n plus 1, and instead of putting the n plus 1 out front, you divide by n plus 1 instead of multiplying by n plus 1. Exactly the opposite. And just for the fun of it here, if we took the derivative of this, we'll call this x to the n plus 1 over n plus 1. If we took the derivative of that, we bring the n plus 1 out front, which will cancel with this, and we'll have x to the n after we subtract 1 from the exponent. The only one you can't do is this one. Make a special note, you don't accidentally try to do this. The power you use cannot be a negative 1. So we have a special case for that one, and it won't be any big surprise. You write it as 1 over x because x to the minus 1 is worthless to you. And we've got a rule for that too. It's called the log rule for integration. This won't be too much of a surprise to you. This will be the natural logarithm of the x. But remember, it's an indefinite integral, so it's one of a family of functions. Next, let's take a look at these two. First of all, let's look at part A. Now remember, one thing you can do right away is you can rewrite this as the derivative of x dx plus, because of the plus right here, the derivative of 2 dx. Oops, forgot the integral. Do these separately. Oh, that was an integral. I messed that up. Let me try that again. So split those up. There, I meant that to be a little bit longer. So x dx plus 2 dx. The x from here, the 2 from there, and the dx with both of them. And then you can do these separately. Remember, this is x to the 1, so you can use the power rule, and this is just a constant, so you just have 2x for this one, and when you're finished, don't forget to put plus c. So here you go. A little bit messy, sorry about that. So that's what you should get. Remember, you increase the exponent by 1, and you also put that number in the denominator. 1 to 2, and also put the 2 in the denominator. And there's your constant of integration on this one. In fact, you could even use this. You could consider this x to the 0 power. So 0 plus 1 is 1, and the 2, we could have just brought that out front, and there's our 2x. And a constant of integration for that one, you can take those two constants, they're just constants, so just call it c. We don't need two constants, then we can use one instead. Like that. Next, part B. Split this up. We've got the integral of this part minus the integral of this part plus the integral of this part. So the 4 becomes a 5. There's your 5. The 5 is also put down here, and there's that 5. And the 3 was already there. We could just slide that out front, and here's our first term. Of course, you could write it just as easily like this. If you like, you could go back a couple of slides here by yourself. See if you can do this, complete everything. It shouldn't be too difficult, really. The 2 becomes a 3. 3 also goes down here, and there's a 5 that was there to begin with, or a minus 5. Your x to the 1 becomes x to the 2, and the 2 also goes down the bottom. And when you put all of those together, put the constant of integration in there because it's an indefinite integral. That means you don't know which of the family of functions it refers to. And there's a good final answer for you. Next, what are we going to do with that? Well, if you remember a couple months ago, we performed some miracles with rewriting functions. So, since this has a square root in the denominator, we use the distributive property and divide that into both those terms in the numerator. So we can rewrite it like this instead, and we can split it up into 2 integrals as well. Using the 1/2, oh, you got that, didn't you? This is x to the 1, this is x to the 1/2. So since you're dividing, you subtract the exponents, there's your x to the 1/2. Basically the same thing here. You've got x to the 0 here, subtracting 1/2, or you can just say bring this up top with 1/2, becomes a minus. Whatever way you like to work it, that gets you the right answer. Once you rewrite it, then you're ready to use the power rule. The difference rule splits it. The power rule gets you a little bit closer, and all that's left really is just a little bit of cleanup work, because you don't leave your answers as complex fractions. In other words, fractions inside of fractions. That's very bad something. It's not good anyway. And there's our final answer. Notice there's one constant of integration for the entire original integral. And we can rewrite this. Remember, this part right here is x to the 1/2. You can factor that x to the 1/2 out of both of these. It's not important, but you could. How about the particular solutions? So far, we've been taking antiderivatives or integrals and ending up with a family of solutions. Well, what about a particular solution? Well, if you have some more information, you can figure out which one it is, because any 2 antiderivatives might be the same, but they'll be vertical translations of each other. That means if this is one, the other one's going to look the same, but it's going to be either above or below the other one, resembling a river in a way, if it's a nice polynomial. Sort of like that. There's a family of functions. We're just looking at some of those millions and millions of functions. Pick any C you like, and you get a particular function in that family of functions. Each of those is a solution of the differential equation. So what we did was we took, where am I? Here we go. So take the integral of that and the integral of this. Got carried away. first thing you do is multiply both sides by dx. 3x squared minus 1 dx. Then you take the integral of both sides. And this will give you y, and that'll give us some function plus the constant of integration. That's the general solution because we don't know what c we need. For a particular solution, we need more information. That's called an initial condition. We've got all these curves, and the big question is, which one? So let's take a look at this one. To find this curve, use the information below. So here's our original function. With the c there, we've gotten this far, but we don't know which c to use. Here's our initial condition. This says the function, when you put a 2 in for the x's, you end up with a 4. So all you need to do is put the 2 in where the x's are. Leave that c there because it is undetermined at the moment. With the 2's in there for x's, it's supposed to equal to a 4. Solve that equation, and you can find out what c is. So the general solution of this one, f of 1 is 2. So the first thing we'll do is integrate to find the general solution, and then use this particular information to find which of those family of functions we're looking for. There's our c. Now we're going to go back up here and use this fact that capital F function, when you put a 1 in for the x, you should end up with a 2. So if we put 1 where those x's are, set this equal to 2, and we'll be able to find out what c is. And in this case, c is a 3. And we've got the particular function from that family of functions. And there's our particular solution. And it shows it over here. This is the information we had, the extra information we had, and we're able to pick out which of those functions we actually were searching for. Each of those represents a solution of that equation. But the black curve is the only one that goes through 1, 2. Sneak back here. It's the only one that goes through that point. None of the others does. And that's using the initial condition along with your integral. So how about an application? We always could use an application. Here's one that if you've taken physics, this should look really familiar. Now it's not just me because I taught physics, but this one, you could say I know this one in my sleep. The S represents height or distance of some kind. T represents elapsed time. And we can use integration to derive that function. So how do we do it? Well, here's our information. We're throwing a ball upward. There's a picture here on a graph. This ball was thrown upward. Of course, as we know, it comes up to an apex, a zenith, and then starts dropping again due to gravity. The question is, can you derive the position function giving the height as a function of t in seconds? When does the ball hit the ground? Two questions. First of all, t equals 0 is the initial time. In other words, that's sort of like As soon as we let go of the ball, we're going to start our stopwatch. So that means the distance at time 0 is 80 feet above the ground. Take a look back here, 80 feet above the ground. Now the initial velocity is 64 feet per second, so that means velocity is ds dt, also known as velocity, also known as s prime, and it's given as 64 feet per second. In other words, that's how fast we can throw the ball up into the air. The acceleration due to gravity is negative 32 feet per second squared. This is the acceleration due to gravity. It's negative because gravity pulls you downward. This is positive because we're throwing it upward. The negative acceleration is what pulls it downward. So the second derivative, notice the two apostrophes up there, that means second derivative of the position function at a time t is negative 32. So if we want to derive that function, we start with the first derivative we can get by taking the integral of the second derivative. This is the second derivative. If we take the integral of it, we get the first derivative. That's how it works. So here we go. We take the derivative of it. This is a constant, so we'll just put that variable next to it. That's pretty easy. And of course the constant of integration. So s prime of t, or the velocity function, is negative 32t plus a constant. Then we know the initial velocity. We threw it at 64 feet per second in the air. So this is equal to 64. And this is also equal to this when t equals 0. Now you can solve that. You can find that this constant of integration is a 64. Next, integrate that one. In other words, you're going to do this and make that curve there. dt, dt. And we've got our velocity function. I'm going to take the integral of that. And we can do that pretty easily. Just one day's practice, some of this will become very easy. The confusion might come when you try to differentiate and integrate on the same day. That's why I suggested the other day in class, you might want to take some good notes, so that when you want to integrate, you look at one set of rules. When you want to differentiate, you look at a different set. You know how to do it, you just don't want to get mixed up between the two. So integrate that s prime of t, or velocity, and there is our distance function, the one we had just a little bit ago. We also know that at time 0, this was equal to 80. So we can solve to get that C2. And there's our answer. Here's what I just showed you in the previous slide. Solve that for C2, you get the 80, and there is our position function. The position function, here's the initial position, the velocity at the start, and this negative 16 represents negative 32 over 2 t t squared. That's what negative 16 is. Because it's actually negative 1/2 gt squared. G is the acceleration due to gravity. G is a negative 32 plus there. And this negative makes it negative 16. Alright, set that equal to 0 and factor that. Set it equal to 0 because where's my cursor? There it is. When the ball hits the ground, the distance is 0. So we set that equal to 0. Now what they did was factor out the negative 16. You might choose to do it in a similar way. When I'm doing that, I actually divide by the negative 16 and I end up with that part. It's a little bit easier to factor. You don't have to worry about the negative 16. Alright, so solve for t with two values for t, but t has to be positive, so throw that out. So the ball hits the ground 5 seconds after you threw it. And that's it for the first lesson in integration. Give it a shot. Try as many questions as you have time for, and I'll see you next in lesson 2 for integration. Bye for now.